So, welcome back to the presentation on monosaccharides. In the previous presentation, we saw what are carbohydrates and the general features of carbohydrates. How do we name carbohydrates? And in the classification of carbohydrates, we saw based upon the complexity, it can be divided into three: monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides are those which are considered to be the simple sugars and which cannot be further hydrolyzed into carbohydrate units. And the basic molecular formula or empirical formula of monosaccharides are strictly CnH2nOn, where N is the number of carbon atoms. Okay, and they are polyhydroxyaldehydes or ketones, that is, it may contain at least two or more hydroxyl groups plus one carbon. It is either in the form of ketone, C double bond O, or it is in the aldehyde form, the CHO. Okay, then smallest monosaccharide, it is composed of three carbon atoms. So N, when we say CnH2nOn as the molecular formula of monosaccharides, the N should be equal to, or it should be more than 3. So that is why smallest monosaccharide is composed of 3 carbon atoms. Okay, you can see over here, this is the simplest monosaccharide. Okay, it contains 2 hydroxyl group. Okay, at least 2 hydroxyl group have to be there on a monosaccharide. So there are 2, obviously. One carbon should be in carbonyl forms. That is, here it is aldehyde form. Okay, this is what is known as a carbonyl. Okay, C double bond O. Okay, carbonyl. This carbon can exist either in aldehyde or in, here you can see, ketone form. C double bond O, it is keto. CHO, it is aldehyde. I hope you have learned in your chemistry classes, right? So this here, few things which you have to see whether the conditions are being met. One is at least 2 hydroxyl groups are there, need to be there in a carbohydrate, in a monosaccharide as well. Okay, and secondly, there should be a carbonyl carbon. Okay, and here it is in aldehyde form. Okay, so when one carbon has to be in aldehyde form, there should be 2 more carbons to take up the hydroxyl groups, isn't it? So there has to be 3 carbon atoms in the smallest monosaccharide node. So that is why this is a structure. Okay, CHO, CHOH, CH2OH. And always when we write, it has to be in this way. Why is it so? Because the most oxidized carbon, that is a carbonyl carbon, has to be written on the top, and it has to be given the number 1. Okay, so this is the carbon 1. Okay, and likewise it goes CHOH till it is CH2OH, CHOH, CH2OH. Okay, now you can see that hydroxyl group, it is attached to the carbon, and here you have a hydrogen, here it is CH2OH. So it makes up the simplest or smallest monosaccharide, glyceraldehyde. Complementary to that, when instead of aldehyde it is having a ketone form, the keto group or the C double bond O group will be in the second position. Okay, while the first and the third position will be occupied by CH2OH. I hope it is okay. Fine. Right, now coming back here, so this kind of a monosaccharide with only 3 carbon atoms, okay, number of, it is known as a triose. And there are one with aldehyde is known as glyceraldehyde, and the other with the ketone group, it is known as a dihydroxyacetone, which we have already mentioned in the previous presentation. With 4 carbon atoms, it forms a tetrosis, and few examples, it is erythrose and threose. They are aldoses, and ketosis, it is erythrulose. Pentoses with 5 carbon atoms, the most important, very well known, it is the ribose, and complementary to that, this ribulose, the ketosis. Okay, hexoses, the most important ones are glucose, mannose, and galactose, which are aldohexoses, while ketohexoses, the most important one being fructose. Okay, these are very few ones which we have mentioned in the table. There are plenty more. Okay, so I hope it is clear. Okay, here you can see the ketosis. Okay, so this is a pictorial representation of all the sugars. Here you can see it is glyceraldehyde, fine, with CHO, HCOH, CH2OH, where the hydroxyl group on the second carbon is on the right side. Okay, we can make the structure of all the sugars from all the aldoses from this particular triose. Okay, the aldo triose. Okay, so here what we do is To make the tetroses, what we do is, maintaining the first, second, and third, we just add another CHOH at this position between the first and the second in aldo trios. Okay, so you can see CHO, it is the same. Okay, just one. Okay, CHO, it is the same, right? Then HCOH, where OH on the right side, that forms the third carbon atom, HCOH. CH2OH, it is the same. Okay. Another HCOH has been added in between the first and the second in aldo trios. Okay, so another molecule has been added. But it can be added in two ways. One where OH is on the right side, and here another where OH is on the left side. Okay, one with the on the right side it forms erythros, and the other with the OH on the left side it forms the trios. Okay, so likewise we get two what you call aldotetroses from glyceraldehyde. Fine. Similarly, from the same erythros we can make two aldopentoses. Again, keeping the first, second, third, and fourth carbons as such, we add an HCOH between the first and second in the aldotetrose. Okay, clear? We are adding another molecule. The rest it is the same. You can see CHO, HCOH, 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 CH2OH. Here also HCOH, HCOH, CH2OH. What we have added? We have added another HCOH in between the first and the second of the erythros. Clear? And it can be in two form, where one where hydroxyl group is on the right side and another where it is on the left side. Okay, so it forms D-ribose and D-arabinose. Likewise here also you can check it. So likewise we can make all the aldoses from the basic structure of glyceraldehyde. Okay, please do write it and learn. Okay, so you start instead of just copying, understand the structure of glyceraldehyde, and then you branch it in this way. Okay, glyceraldehyde divided into two, add the HCOH group anew. Okay, one where hydroxyl is on the right side and the other on the left side. You make the structure in this way. Fine, and then you start learning. Okay, it will be easy then. So these are the what you call monosaccharide structures. Okay, now coming back to the structure over here, you can see that some of the carbons in the chains, they are given in pink color, isn't it? So what is the significance? You can see in the glyceraldehyde, uh, this carbon, the first carbon, I hope you know that carbon is having four valencies, and when all the four valencies are like filled with different molecules, we call such a carbon as asymmetric carbon. Okay, and whenever carbon try to form compounds, it tries to fill all the four valencies, isn't it? So here you can see the first carbon, it is filled with the valencies are filled with one hydrogen, two with oxygen, and one with CHOH, CH2OH molecule, isn't it? So here what happens, since two valencies are filled with the same molecule, same group actually, this carbon is not asymmetric. What about this one? One valency with CHO, one valency with hydrogen, one valency with hydroxyl, and the fourth one with CH2OH. So since all the four are completely different groups, this carbon is referred as a asymmetric carbon. What about this one? Okay, here you can see this one. Okay, the third carbon of the glyceraldehyde, I have written it this way. Two valencies are filled with the same molecule, hydrogen. So it is again not asymmetric. Okay, so what about this one? Okay, CHO we have already seen. CH2OH also we have already seen. It is, they are not uh, asymmetric. This one, it is asymmetric because carbon, hydrogen, CHO actually we have to take in that way. Okay, CHO, hydrogen, hydroxyl, CHOH, CH2OH. So this is asymmetric. What about this one? It is CHOH, CHO, then CH2OH, hydroxyl, and hydrogen. So again, this is also asymmetric. Okay. So likewise, if we check all those pink colored carbons, they are all asymmetric carbons, or what we refer as the chiral carbon. Okay, I hope you know. How do you chirality and chiral carbon? You may have learned it in your chemistry classes. Okay, this is chiral. So it is chiral carbon. Fine. So, they are known as asymmetric carbon. what is asymmetric carbon? Asymmetric carbon is one where the 4 valencies are filled with 4 different groups. Okay, so you can see in triose we have only one. In glyceraldehyde specifically. What about this one? Ketosis. They don't have. Dihydroxyacetone doesn't have any chiral carbon. Okay, and here in 4 carbon atoms, 2. 2 asymmetric. Here also 2, and here there's only 1. So you can see in aldohexoses, whatever be the number of asymmetric carbon, it is just 1 less in the case of the corresponding ketosis. Okay, it do have a very important property because chiral carbon or the presence of asymmetric carbon can result in isomerism. You may have learned it. Mirror forms and all can be formed, isn't it? So isomerism. So isomerism is a very important property of monosaccharides, and it is because of the presence of these asymmetric carbons in their chain. Okay, and this is what is known as the open chain, or what you call, oh sorry, open chain, or it is known as the uh, straight chain. Okay, and obviously what happens is there are different properties which are completely depend on the open chain property. Okay, open chain existence of monosaccharides. Okay, so these are the different molecules, and here what you are supposed to learn is you have to study the structure of glyceraldehyde, the triose, then erythrose, which is a very, again, an important molecule. So all these molecules are which are given in squares. It is very important. Okay, and another thing we can see is the ribose. It is very important structural molecule in the case of the nucleic acids, nucleotides, nucleic acids, etc. Okay, and this one, glucose, again, it is a very important molecule, one of the most abundant source of energy in animals, glucose. Okay, D-mannose and D-galactose, and you can see here in the glucose structure you have to learn, because most of the properties and even the disaccharides and polysaccharides are based on glucose. Okay, so you have to learn the structure of glucose. So you can see here all the asymmetric carbons do have hydroxyl groups on the right side except the third one. I hope you remember the numbering. Okay, the most oxidized carbon will be getting the number 1, and it will be written on the top. Okay, while the reduced forms will be, I mean, the rest of the chains will be written in this way. Okay, so here it is a C1, C2, C3, and it is a C3 which is having the hydroxyl groups on the left side. The rest of the carbons, asymmetric carbons, do have hydroxyl on the right side. Okay, so this is the basic structure of glucose. If you learn glucose, you will be able to learn mannose as well as galactose. You just need to compare. You can see in the case of mannose, what is the difference? The all the carbons remaining the same with the groups arranged around them. The second carbon is having hydroxyl on the left side, while it is on the right side in the glucose. Okay, the rest is the same. Right? In galactose, when you compare it with glucose, the fourth carbon is having hydroxyl on this side, on the left side, while the rest it is the same as that of the glucose. Okay, so glucose, mannose, and galactose, slight changes with respect to the position of the hydroxyl and the hydrogen. Okay, that is the first thing. Secondly, if you see, all these are being named as D forms. So that D-glyceraldehyde, D-erythrose, D-ribose, D-glucose. Okay, why is it so? It is based upon the position of the hydroxyl group on the most, you can see, the asymmetric carbon which is farthest from the oxidized carbon, which we have already learned in the previous presentation, but we can see that here, just we'll take one example, glucose. Okay, so this is the most oxidized carbon, right, and which is the farthest asymmetric carbon from the oxidized carbon. This is this one, C5. Okay, so what we do is we look at the position of the hydroxyl group on the C5. If it is on the right side, we name it as D form, and if it is on the left side, we name it as a L form. Okay, in all these, it is on the right side. Okay, you can see, right? So the carbon which is closest to CH2OH, the last carbon. Okay, or the what you call carbon which is the asymmetric carbon which is farthest from the most oxidized carbon. Okay, so there you have to check the position of the hydroxyl group, and if it is on the right side, we name it as D form, and if it is on the left side, we name it as a L form. L for left, we can, like, just for understanding it, remembering, you can write it as